Now we're going to look at a different type of problem. This is a problem where you are given the reactant and the reagents and then asked to fill in the product. For doing something like this, once again, you have to know your reactions. And so if you don't have them organized, then this is going to be a big problem for you. Now, just as in the problems where you were having to fill in the reagents, you would like to try your best to minimize the number of structures that you draw. So keeping all of that in mind as you're carrying out these problems, keep thinking about, well, where do I have to draw everything? Or can I just draw a few things and then draw the final answer so I can get this done as quickly as possible? So for instance, in this situation, what I'll do is I'll go ahead and draw out everything, but keeping in mind that you don't have to do this. So after step one, instead of alkenes here, I'm going to have added HCl, and notice that I'm adding HCl with peroxides. So I'm not, remember when you add HCl and peroxides, the chlorine in this case and the hydrogen are going to go to specific carbons. In this situation, the chlorine is going to end up on the carbon where if I was looking at a partial positive charge or a carbocation, the chlorine goes to the carbons that are less substituted, have less alkyl substituents in this situation. Once again, if you are not following this, then you need to go back to look, where do I have the mechanism written out for adding HX with peroxides to a carbon-carbon double bond? So that's the first product. KOH and ETOH, what that does is that does a dehydrohalogenation reaction on alkyl halides. Well, turns out that the only product that can be formed in this case is this one. When you carry out the dehydrohalogenation, you lose a chlorine and a hydrogen on an adjacent carbon. There are no hydrogens on this carbon, so you can't form the double bond here. For this here, I can only lose this chlorine and this hydrogen on that carbon. There are no other places to form the carbon-carbon double bond. So these two steps, you may have been able to imagine having the chlorine on this carbon, having the chlorine on this carbon, and then, okay, now I'm losing a chlorine and an H, so I go, oh, I get back to the same thing. So maybe you wouldn't have had to draw this out, is kind of the take-home message. Well, now, these two steps comprise an ozonolysis reaction. So you might remember in an ozonolysis reaction, I am cleaving the carbon-carbon double bonds and adding a double bond O to all of the carbons of the carbon-carbon double bonds. So the easiest way to show that is to put a double bond O at the end there. This bond is now going to be broken, and there will be a double bond O on this carbon and a double bond O on that carbon. And then finally, when you cleave this carbon-carbon double bond, there is also another compound there. And so that is the final answer. Once again, if you can, you want to try your best to minimize the number of structures that you're going to draw. So once again, some advice for you. 1, minimize the number of structures. And 2, you will usually need to make some sort of decision. So for instance, here, the decision was, in the first step, where does the H and the chlorine go on both of these carbon-carbon double bonds? Decision here in the second step was, where does the double bond form?